Previously, I told you about gas chromatography mass spectrometry, which is a way we can separate compounds and analyze them and determine unknowns. But primarily, those are organic compounds. And when I say organic, I mean carbon, hydrogen, oxygen, nitrogen-containing compounds. But they have to be semi-volatile or volatile, which means they have to boil somewhere between 0 and 300 degrees Celsius. If a compound is non-volatile, or if it's polar, doesn't boil in that range, we use a light process, which is separation by liquid chromatography, and detection again by mass spectrometry. So liquid chromatography separates those non-volatile and polar species using a chromatographic column, and instead of being carried through and separation based on boiling point, the separation occurs based on its affinity for the solid phase material in the column. So we start with a number of samples here. We might have an entire rack. You see many, many samples there being analyzed. This is an auto-sampler. The robot will go over and pick up a sample, select it, put it into an injector. The injector will run it through a micro column, and then it will go through a separation column here, which separates the analytes. The affinity for the solid phase material is what causes one analyte to stay on column longer than another analyte. After it goes to that column and separated, each one of these are analyzed by an ion trap mass spectrometer, the same kind of mass spectrometer that I showed you with the GCMS. So after the samples are separated, the analytes are separated, we have to ionize them, because again it's based on a mass to charge ratio, and a charge requires an ion. So we're going to take that analyte and attach an ion to it. Inside is a very, very small needle which is heated, and we put an electric current on that needle. And that needle causes a charge to be attached to our analyte ions. After it's charged, we can separate based on the mass to charge ratio using an ion trap, again allowing us to do MS, MS, MS as many times as we want for an analyte, taking the original molecule, breaking it up, selecting a fragment, breaking that up, doing it as many times as we need to get the selectivity we need to make sure it's only for that analyte. So the types of analytes that we would look for by LCMS are generally the metabolites. The active ingredients we might analyze by GCMS, pesticides, PCBs, dioxins, etc. But many of those analytes we would analyze by LCMS, because when the body metabolizes it, it usually makes it non-volatile and more polar. That way we can eliminate it. So if we're going to analyze, and we may analyze in serum, or we may analyze in urine, but we would analyze on the LCMS. One of the projects that we're looking at right now are compounds which are metabolized after you eat them. And these compounds, ziranols, we think have estrogenic properties. They're from grain mycotoxins, and you would get them from eating everything from popcorn to beef. But we don't know how much people are getting. And so we're analyzing this, especially in people, young people, our kids who are developing and may see a greater effect from these compounds when they eat them. Another class of compounds that we analyze right now are bile acids. Bile acids are produced in the liver and are transferred. They create what we call, or are part of, our gut microbiome. So we can differentiate some disease states based on the ratios of some of these bile acids. We've developed an assay to monitor these bile acids not just in the gut fluids, but also in the tissues that produce them and the tissues where they wind up. We hope to be able to differentiate and get some disease biomarkers from some of this work.